Hi everyone, my name is Dahibat Bhatt. In this work, we present FCAL, a calibration method proposed to train probabilistic neural regressors. Aleatoric uncertainty is inherent in the data and it cannot be reduced. It can only be estimated. In this work, we aim to obtain calibrated estimates of aleatoric uncertainty. In this illustration, we see ground truth bounding box in figure A. Figure B shows an overconfident prediction as denoted by small ellipses. Figure C shows underconfident and highly inflated uncertainty estimate, which is consistent in terms of probabilistic prediction but not calibrated. Figure D shows correct uncertainty estimate reflecting variance of underlying data distribution. In typical probabilistic neural regressors, aleatoric uncertainty is modeled as Gaussian distribution, and negative log likelihood of Gaussian is used as the objective function to train the neural regressor. Predicted uncertainties are generally over or underconfident and they lack calibration. In this work, to enforce distribution and calibration constraint, we fuse a set of k standard normal random variables to create a chi-squared random variable. For k greater than 50, the chi-squared distribution converges to Gaussian distribution according to central limit theorem. In our algorithm, a neural regressor predicts mean and standard deviation for an input, and we calculate residuals and create chi-squared hyperconstraints. We employ F divergence to match it with the desired target distribution. Given a batch of input data, the model predicts mean and corresponding uncertainties standard deviations. We calculate empirical loss such as mean squared error or smooth L1 as well as distributional matching loss to enforce calibration and train the model. To evaluate calibration performance, we use expected calibration error. ECE or expected calibration error Z evaluates whether a sample prediction follows a Gaussian distribution or the residual follows a standard normal distribution. And ECE chi-squared, also denoted as ECEQ, evaluates whether a collection of sample predictions in a batch collectively follow a chi-squared distribution as a result of central limit theorem. Now we present quantitative results of FCAL. We compare FCAL against various different baselines for different tasks and see that it yields optimal ECEZ and ECEQ values, which are metrics used to evaluate quality of calibration. Unlike bouquet dataset, we observe that there is a stronger trade-off between deterministic and calibration performances for the depth estimation task. We analyze this by plotting calibration versus deterministic performance and establish that FCAL-based method yields better calibration compared to the baselines. We believe that this trade-off observed is due to the discrepancy between true aleatoric noise distribution and the canonical modeling assumption. We introduce a distributional match for our toy setup and we verify this hypothesis. Here we show qualitative results for the task of depth estimation on kitted dataset. We can observe that the depth uncertainty is highest near object discontinuities, which makes sense intuitively. Now we show qualitative results of FCAL on kitted dataset for object detection. In this temporal sequence, we could observe that FCAL yields higher uncertainty estimates for occluded cars, which are difficult to identify, and yields confident predictions for objects with better visibility. In conclusion, we propose a variational method to calibrate aleatoric uncertainty. We yield state-of-the-art results across a variety of tasks. We perform analysis of accuracy versus calibration trade-off. We show that FCAL can be easily implemented in 10 to 15 lines of code and can yield state-of-the-art calibration results without the need of post-hoc optimization or a held-out calibration dataset. We thank you for listening to this. For more details, please visit fcal.github.io.